Hello everybody, we are team number 29 and let us introduce the result of our work named Extreme Sparsity by Input Convex Neural Networks. First of all, I'll tell you about the problem statement, then about theory, and after that I will tell you about our experimental results. So let's start. It is known from calculus that every function can be represented as a sum of convex and concave functions. And a neural network is a function, so it can also be considered this way. To achieve this, we can assume that inner states of the neural network are convex, but the last one with arbitrary weights will correspond to the linear combination of convex and concave functions. This process is connected with zeroing some elements, so it can end up with obtaining a sparse version of neural networks. So we conducted the experiments for this kind of neural network and compared its performance with vanilla neural networks and also measured index of sparsity. There are two requirements that form the sufficient condition for a neural network to be convex with respect to its input. Here they are. First, activations are convex and non-decreasing. Second, all weights are non-negative. In our work, we will maintain explicitly these requirements during neural network initialization and training process. We trained classical models and convex versions for different tasks, for example, image classification or image segmentation. Then, we evaluated their performance on corresponding datasets. If a neural network contains dense layers, then L1 regularization was applied to both convex and non-convex models and sparsity index was compared. We considered 5 types of architectures and datasets for them. FCNN on MNIST, convolutional autoencoder on CELEB-A, convolutional neural network on cats dogs dataset, ResNet-18 on CIFAR-10 dataset, and UNet on lung CT segmentation. To achieve convexity after each backward pass, we turned weight non-negative using ReLU function. Now I will tell you about the experiments and obtained results. First of all, we conducted the experiments on MNIST dataset. We used a 4-layer neural network with the following architecture. When we construct the convex version, we constrained the second and the third layer to be non-negative. MNIST dataset consists of 60,000 images corresponding to 10 classes. We considered both types of inner convex neural networks with skip connections and without them. The architecture with skip connections showed better performance, however, it is more complicated and doesn't solve the main problem of this work, sparsity. As you can see, the inner convexity ended up with loss of accuracy. However, we were able to achieve 59% of sparsity. For this task, we have chosen a simple convolutional AlexNet-like model with input size 64 by 64. The model consists of 2 blocks of convolutional ReLU activation max pooling and batch norm layers, after which the result is flattened and passed to 2 linear layers. To turn convolutional neural network into inner conv network, and all the dense layers except the last one are turned to post-dense. All the convolutional layers except the first one are turned to post-conv two-dimensional layer. To train the model, we augmented the trained data using random rotation, random resized crop, random horizontal flip transformations. Pictures of the dataset were resized to the size of 64 by 64 and normalized before being processed by the model. The results are following. The results show that inner convex neural network learns slower than a classical neural network. It showed larger loss and smaller accuracy at the epoch 50. However, their learning curves show that if they trained more, higher results can be achieved. The other interesting result is that with L1 regularization, the inner convex network sparsity increases drastically, while the quality matrix result maintains almost the same. LungCT is a dataset from Kaggle competition used for binary segmentation. It consists of 200 single-channel CT images with corresponding masks. In the task, we use a U-Net-like architecture, but we replaced transpose convolution to unpooling layer and added batch norm to each block. The results can be seen here. Even though the convex U-Net results are slightly worse, its high sparsity rate, 0.42 versus 0, tells us that the inference time for the convex network will be much less. ResNet is a convolutional neural network with shortcut connections. In this work, we considered the ResNet 18 neural network with 18 layers. We used its implementation from PyTorch. The experiments were conducted on CIFAR-10 dataset. As we can see, the inner specification ended up with the lower accuracy. However, with L1 regularization, it helped to achieve 95% of sparsity. This is almost the state-of-the-art result. To test this approach in field of autoencoders, we considered a simple convolutional autoencoder consisting of 2 convolutional and 2 linear layers in the encoder and 2 linear layers in the decoder. CeLU acted as activation with satisfied restrictions by our approach. The performance was evaluated on the CeLab-A dataset reduced to 40,000 images due to Google Colab technical limitations. Pictures of the dataset were resized to the size of 64 by 64 and normalized before being processed by the model. The inner convex modification fell short in terms of MSE on validation, 0.03 versus 0.01, and the sparsity of both inner convex and inner convex L1 regularized variants were lower than expected. Let me now sum up our results. One of the most impressive facts that were found is that in contrast to classical dense neural networks, L1 regularization, which is applied to convex models, can achieve significant sparsity rate. In some cases, the combination of inner convexity and L1 regularization allows to achieve nearly state-of-the-art performance in terms of sparsity. However, in some cases, it reduces performance without any significant sparsity. This fact needs to be studied further. The sparsity with this inner convex concept can become a very useful option, which can be also optimized to reduce learning complexity. However, as soon as the sparsity in this case increases naturally, it should be examined under what conditions it will work efficiently. Thank you for your attention. This is the end of our presentation.